Hello, ladies and gentlemen. We're going to do 3.6 today. We're going to be analyzing functions. And then the additional caveat is that we're going to take that analytical process and then we're going to use it to sketch the graph of a curve without using our calculators. So we have some general guidelines and things that we need to do to help us analyze a function. One is we like to determine our domain and range. So sometimes I don't need those, but it is helpful, especially if you have a restricted domain. Number two, we're going to find intercepts. Then we're going to look at our asymptotes in case the function has any. And then we might also consider symmetry. Alrighty. The third thing that we're going to do is we're going to take the first derivative and we're going to set it equal to 0 and we're going to find our critical points. And remember that we are using the first derivative test to test for intervals where our function is increasing, decreasing, or constant. Okay. Alrighty, and then the next one obviously would be to do the second derivative test. We're going to also set it equal to 0, find those critical points in case there are some that are different. And remember that our second derivative test is going to be used to find intervals of concavity, can't spell that. We're also going to be looking for points of inflection. And then we'll take all of this information and we'll use that information to help us solve a problem. All right, so I'm going to start a new sheet so we can do kind of a longer example. And the example is going to say analyze and sketch the graph of, and we're going to be given the function f of x is equal to x to the fourth minus 12x cubed plus 48x squared minus 64x. So I know a lot about this function already. I know in theory that the domain is going to be all reals. The range I'm not so sure about, so I'm just going to not do that one right now. The x-intercepts, you're going to have to trust me a little bit. So I'm going to tell you that the x-intercepts are going to be 0 and 4 with a multiplicity of 3. And I could get that by factoring. So I could take an x out, then I'm down to a cubic function, and then I could do grouping and I could factor. And it actually turns out to be a perfect trinomial. That's the wrong word, a perfect cube. And so then I could factor that way, but we're going to skip that at this point, and I'm just going to let you trust me that these are my intercepts. I know that because it's to the fourth degree and that the leading coefficient is positive, that its end behavior is probably going to look something like that. I don't have a y-intercept, so it's possible that it goes through the origin, but not 100% sure. Okay, so I'm not going to write that down. Now I'm going to take my first derivative, and I'm going to get 4x cubed minus 36x squared plus 96x minus 64. And I'm going to set that equal to 0, and I'm going to solve for x. And again, I could factor out a 4, and then I could do some grouping, and I could do some factoring work. And if I did that, I would find that my critical values are going to be 1 and 4. And I'm going to assume at this point that you guys can do that work. If not, you can come see me and we'll work on it together. But you could find those critical values of 1 and 4. Well, then I'm going to take my second derivative, and I'm going to get 12x squared minus 72x plus 96. Set that little guy equal to 0. Factor out the 12 and factor, and I'm going to get that these critical values are 2 and 4. Okay, so these are my critical values. For me, it's helpful to see it on a number line for my critical values. I'm not going to put my x-intercepts on the graph. I'm just going to put my critical values. So I have 1, 2, and 4. So what that does is it helps me create the intervals that we're going to be doing some math on. Alrighty, so I'm going to drop all of this information into a table. And I've changed it a little bit from last year on how I manage it, and I think this works better. So my first interval is going to be from a negative infinity to 1. And I'm going to draw a little guy. And then my next one is from 1 to 2. And then I'm going to consider what happens from 2 to 4. And then I'm going to consider what happens from 4 to positive infinity. All right? And that's going to be my table. Alrighty, so now I'm going to evaluate my function, okay? And what I'm going to do when I evaluate the function is I'm going to evaluate these endpoints because I'm going to have it help me look at my extrema. So if I evaluate f of 1, I get a negative 27. And if I evaluate f of 2, I would get a negative 16. And I know that's a lot of work that I'm not doing, but I'm assuming that you could use your calculator to help you do that math. You just can't look at the graph. And then I would do f of 4 is equal to 0. And then I don't need to evaluate this one, okay? So that's my first evaluation point. You'll notice that I have a minimum right there at a negative 27, okay? So I'm just going to write that in my little table. Now I'm going to put in my derivative, and I'm going to actually go back to my derivative, and I'm going to write x minus 1, and we had 4 with a multiplicity of 3, so I'm going to write x minus 4, and I'm going to make it be there, okay? So remember when I'm doing a sign chart, and I actually don't want to do that, so sorry, my bad. I'm going to do it this way, okay? I want to substitute in values, and so I might do a negative 10, I might do a 1/2, I might do a 3, and I might do a positive 10, and those would be the values that I'm going to evaluate. Well, when I evaluate my derivative at a negative 10, it turns out that it's negative, and you can either run it back through the function or you can run it through here, okay? And at this point, I think a negative, it would be easier to run it through here, but all I'm really concerned about is the negative, which means that my function is decreasing. If I run a 1/2 in this interval through the function, I'm going to get a positive value, which means that my function is increasing. Well, right here, you'll notice I go from a decreasing tangent to an increasing tangent, so that means I have a minimum right there, okay, which just confirms what we found there. And then in this interval, I'm going to find that it's increasing, and in this interval, I'm going to find that it's increasing, okay? And I'm just going to draw a line, and then I'm going to do my second derivative, okay? If I substitute in same intervals, right, a negative 10 into my second derivative, I'm going to get positive, which means that my function is concave up. And the second one, I'm going to get that it's also still concave up, which means that there's no change in concavity, so there's no inflection point at x is equal to 1. In the third interval, I'm going to get a negative, and so that tells me that I have concave down, which means that I have an inflection point at x is equal to 2. Okay, scoot it up just a little bit. I thought I gave myself enough room. And then in this last one, I have this is positive, this is concave up, and so I have another inflection point. And this one is going to be at x is equal to 4. So if I really like this method, I think that it's a nice and polite way to organize, and it actually gives you a nice visual of your graph. So now let's write down our analyze. I hate spelling this word because I always spell it wrong. So scribble that out, A-N-A-L-Y. Can't spell it unless I say it. So I'm going to analyze as we go across. So the first thing that I'm going to write is that I have a relative minimum at x is equal to 1, okay? I know that my function decreases from a negative infinity to 1, okay? I know that my function increases from 1 to 2, and then from 2 to 4, and then from 4 to positive infinity, but that seems a little bit silly, so I'm going to say it increases from 1 to positive infinity, okay? And I'm going to draw a line through that because I'm just managing the information that I have. I'm going to talk about my concavity next, so I know that my function is concave up in the interval from a negative infinity to 2. I have an inflection point at x is equal to 2 if I wanted to find the y value. So if I actually wanted to find the coordinates of the point, to find the actual inflection point, I would take this 2 and I would run it through the function to find the y value. And notice that's the original function and not any derivatives. And then I know that my function is concave down from the interval from 2 to 4, and I have an inflection point at x is equal to 4, okay? And again, if I wanted to find the value of the inflection point, then I would run the 4 through the function. So I would do f of 4, and then that value would become the y value for the inflection point. And then I know that my function is concave up, concave up from 4 to positive infinity. Alrighty? Well, if I take all of that information and I put it on a graph and I do it very carefully, we knew that the minimum was at 1, negative 27. So that sucker would be way down here at a negative 27. So I'm going to put a dot there. Okay. I could find my zeros. We said that I had a 0 at x is equal to 0, so I know it's going to cross there. And then 2, 3, 4, I have another 0, and it's been down here, so it's been decreasing, decreasing, increasing. So I'm going to guess, oops, I missed, that my function's going to do something like that. Okay, not a perfect model, but close. I did have a change in concavity right here, so maybe I need to fix my curvature a little bit, but I get a general idea about what my function looks like. So that's it. I'm just going to do the one example, and then I think we'll be good for today. See you soon.